Hello everybody, my name is Chad Sharp, and I'll be presenting Alchemy, a language and compiler for homomorphic encryption made easy. My co-authors are Chris Pikert and Eric Crockett, and we are, or at one time have been, from the University of Michigan. Okay, so before I start talking about what Alchemy is and how it makes implementing homomorphic computations easier, I should first describe what fully homomorphic encryption is, although if you've been in this room for a long enough period of time, or you were here for the keynote speech, you already have at least somewhat of an idea. So traditional encryption schemes consist of three algorithms: a key generation algorithm, an encryption algorithm for turning plaintexts into ciphertexts, and a decryption algorithm for turning ciphertexts back into plaintexts. Sort of crypto 101 here. But fully homomorphic encryption schemes add one more operation, one more algorithm called eval, which, given a function f and a ciphertext x, compute f homomorphically on x, which ultimately yields a ciphertext of f of x. So what this allows us to do is perform arbitrary computations on ciphertexts without ever leaking the underlying data or without requiring the key. So this has long been considered the holy grail of cryptography, back since 1978 with Revest and Shamir. The first plausible proposal was in 2009. Prior to that, many believed that it wasn't even possible, but the first plausible proposition was in 2009. It has since become a very active area of research, as you've seen today. So the sort of model here is that we have a client who encrypts some data, takes x, turns it into a ciphertext x. He sends this to the server. The server evaluates some function f and gets back an encrypted f of x. Sends this back to the client. The client can decrypt the encrypted f of x and get back a plaintext f of x. So the client both does not have to sacrifice their own computational resources to perform this computation, nor do they have to sacrifice their privacy. So this sounds like a great idea. You've heard it hyped up a lot today. So why? So you may want to implement this. You may want to implement this yourself. And as we heard in the keynote today, it's maybe not so easy. So suppose we wanted to implement this computation here. This computation f, taking three arguments, x, y, and z, that computes x plus y squared times z. Suppose we want to implement this homomorphically. This is currently a computation on plaintexts. We want to turn it into a computation on ciphertexts. So the first thing we're going to have to do is express the computation in the native instruction set of whichever FAG scheme we're targeting. So as it turns out here, this is pretty easy since all FAG schemes support both addition and multiplication. But for more complicated computation, this may be more difficult. It's often easiest to think of this in terms of a circuit, as you see here, mostly for visual purposes. So the next thing we're going to have to do is, as we do operations on these ciphertexts, each ciphertext has this intrinsic property called noise. And as we do operations on the ciphertexts, the noise within them grows. And if the noise level gets too high, then we won't be able to decrypt at the end, or we won't decrypt successfully. And so we have to add these maintenance operations. In this case, they're called key switch and mod switch, which reduce the noise of the ciphertext as we go through the computation. We also have to generate and manage keys and hints. The generation and management of keys isn't super surprising. This is something that we have to do in traditional encryption schemes too. The only difference here is that there's also this additional notion of hints, which are an additional parameter to those maintenance operations that I described earlier. And what is probably the most difficult of the hurdles here is at each step in the computation, we have to track what the noise level of these ciphertexts are. So I'm taking y and multiplying it by y. I have to know what the noise levels of those y's are and know what the ultimate noise level is going to be after I multiply them. And you have to track this for each operation that you do during the computation, and this requires a fair amount of expertise, both in the theory of FAG and the specific implementation. And finally, once we've expressed it in terms of the native instruction set and added all these operations, now we actually get to write the code. So you can see here, this is what that initial computation might look like now after we've done all this stuff. And we have to target one particular FAG implementation. So some examples here: HElib, CL, Palisade, and LOL. LOL is the one that Alchemy currently targets, so that's the one that I'll probably reference the most for the remainder of this talk. And so we can see that the code, both in terms of just simply the amount of code that you have to write, but also sort of the cognitive overhead, the understanding that is required to implement this computation blew up from start to finish after each one of those steps. And so we started off, we thought we were implementing something more along the lines of this, and it ended up looking more like this. And so this is one of the principal reasons, as was mentioned in the keynote today, why homomorphic computation or why homomorphic encryption isn't more popular. And because the result of this is that implementing homomorphic computations is accessible only to experts both in the theory of FHE and the specific implementation. And so what ALCHEMY is trying to do is we're taking a systematic approach using languages and compilers to reduce the burden on the programmer. So we want to make it easier for the programmer to write these FHE computations. And so in order to do that, ALCHEMY consists of modular and extensible domain-specific languages for both plaintext and homomorphic ciphertext computations. Each of these DSLs can be fed to one of many interpreters, many of which compose together. The heart of ALCHEMY is a compiler that transforms plaintext computations into homomorphic ones, taking care of most of the grunge work that we mentioned earlier. And the ultimate result of this is that the programmer can write what they care about, which is the plaintext computation. So, in order to, before I go on talking about ALCHEMY, in order to demonstrate that ALCHEMY is at least in some respects practical, we've implemented a testbed application using it. We've homomorphically evaluated a ring WR based pseudorandom function, which has previously been recognized to have a strong fits with FHE. Our unoptimized implementation achieves a roughly 2 order of magnitude improvement in latency over prior state-of-the-art implementations of other PRFs, I should say. The implementation and the resulting implementation is quite short, only coming in at roughly 20 lines of code. Only coming in at roughly 20 lines of code, and the resulting implementation is fairly clean. So. We'll get to that in a bit, get some more details on that in a bit, but now let's take a step back and talk about ALCHEMY's plaintext ciphertext compiler and see how it addresses those hurdles that I mentioned earlier. So the first thing that we had to do was express the computation in the FHE scheme's instruction set. In many ways, this can be thought of sort of as writing assembly code. The FHE scheme has some set of instructions, but really you ultimately want to implement some sort of higher level computation. And so what ALCHEMY does is it exports a library of higher level operations. Obviously, this could do to be expanded. And what this allows you to do is write ultimately higher level code. However, this library of higher level operations needs to be expanded. So I can't in good conscience say that this is completely solved in its current state. However, ALCHEMY does automatically insert all maintenance operations and automatically manage and generate the necessary keys and hints. And additionally here, and probably the most important thing that it does is it statically tracks the noise of each ciphertext. This is actually encoded in a type system in the language in which ALCHEMY is implemented. And it statically ensures the validity and security of the parameters that are chosen. The only thing the programmer needs to do is give ALCHEMY a pool of parameters from which to choose, and it picks combinations of those parameters and inserts them into the computation where necessary. And finally, it ultimately does output a computation that can be evaluated on ciphertext. In this case, it targets LOL specifically, but it's extensible enough that it can support any of the other implementations that I mentioned earlier. Okay, so we talked about ALCHEMY's plaintext ciphertext compiler. Let's take a slight step back and talk about a little bit more generally what ALCHEMY does and can do, and how using ALCHEMY might look. So ALCHEMY, as I mentioned, has several what are called interpreters for its DSLs. One of them is just a simple evaluation interpreter. So given that simple circuit that we talked about earlier, that computation on plaintext F and a plaintext X, it can give us back the plaintext F of X. This is decently simple. We can see here what that looks like implemented in ALCHEMY's DSL. So we create a function here that's nearly identical to the one that we created earlier, x plus y squared times z. We evaluate it and we get our expected 95. Now, there's nothing too crazy there. But here we can see ALCHEMY's plaintext ciphertext compiler at work. So the PT to CT, the plaintext to ciphertext, gets that simple computation on plaintext, as well as this pool of parameters, Q1, Q2, etc. And it outputs two things. It outputs the keys that it generated during the compilation process, as well as the more complicated computation on ciphertext. We can then feed this computation on ciphertext to our evaluation to our eval interpreter, give it a ciphertext x, and we'll get back a ciphertext f of x. We can then decrypt that. We can decrypt the ciphertext f of x using our generated keys and get back a plaintext f of x. And we can see that PT to CT and eval here compose directly. But suppose we also wanted to. Excuse me, I'm getting ahead of myself. Let's see what the code looks like for that. So the first thing that I want you to notice is that this first line where we define f didn't change at all. So we wrote the plaintext computation one time, and then we can interpret it multiple ways. We can evaluate it, we can compile it, we can do whatever we want. The next step is we compile f so that into a homomorphic computation on ciphertext, we get back our homomorphic computation CTF as well as the keys that were generated. We then encrypt our arguments using those keys, and then eventually we can evaluate our homomorphic computation, decrypt it, and get our expected result of 95. Okay, but suppose we also want to add some diagnostic information to the computation as well. Well, Alchemy has an interpreter for that, and once again, it composes with both PT to CT and eval. In fact, it sits right between them. So our write error rates interpreter gets the complex computation on ciphertext, the homomorphic computation on ciphertext, excuse me, and as well as the keys. And what it outputs is a computation that not only can be evaluated to get a result, but also keeps a diagnostic log throughout the duration of the computation, such that when we give this to eval and evaluate it, we end up with a diagnostic log at the end. I just noticed though there's a bug in my diagram. This should have a red line around it. It's because it's a ciphertext x. Not sure how that happened. Okay. Anyway. And once again, the code didn't change substantially. So we still have written the same f, the same plaintext computation at the top. The only difference here is we've composed write error rates in PT to CT. And then down here, instead of just getting a result, we get both a result and a diagnostic log. And so we can see what this diagnostic log looks like right here. And basically, all this is along the left-hand side, we can see what operations were done throughout the computation. So mul, add, mul, those were all written by us, but Alchemy inserted mod switch, etc. We can also see the parameters that were chosen. That's those Qs are right there. And then finally, on the right-hand side, we can see what the noise rate was, the noise level in the ciphertext was at each level of the computation. And unsurprisingly, as the computation went on, this noise rate went up. But that's totally fine because Alchemy managed the parameters accordingly, so it was still low enough that at the end of the computation, we could decrypt successfully. We also have a couple other interpreters that could have taken the place of eval there before. So if you didn't want to get the result, you can use our not so pretty printer, which outputs a sort of lambda calculus-like representation of the computation. There's one that just simply outputs the parameters that Alchemy selected, and one that outputs the expression size rather than evaluating it. And so I'll expand upon that to some extent here, where I talk about the language and the broader design of the DSLs and their interpreters and how they interact with one another. So Alchemy follows the type tagless final style, which is basically just a method of implementing domain-specific languages that ensures modularity and extensibility. The DSLs are composed of what are called language features, and each of these can be combined arbitrarily by expressions. And this may seem kind of vague right now, but we'll get to exactly what I mean here in a second. Some of these features might be arithmetic, user-defined functions, conditionals, FHE operations, etc. And then each of these features defines an interface for interpreters to implement. So what do I mean by that? Okay, so here are some language features, and along with each of them is their interface. So arithmetic, the interface for arithmetic is plus and times. And then each expression can sort of combine these features together. So the expression here, that's a function that doubles its argument. It uses the user-defined functions language feature as well as the arithmetic language feature in the form of lam and plus, respectively. Additionally, here we can see that this expression creates a user-defined function. It uses some FHE operations and uses the arithmetic language feature since we're multiplying two ciphertexts together. And so then each of these interpreters has a set of these language features that it supports. So PT2CT can operate on any expression that uses the arithmetic and functions language feature. But of course, what PT2CT ultimately outputs is another expression. And what PT2CT does is compile a plaintext computation into a homomorphic one in ciphertext, and so it inserts those FHE operations that we mentioned earlier, like key switch and mod switch. And so it outputs an expression that has arithmetic, user-defined functions, and FHE operations. And so any other interpreter that I compose with this needs to support those same language features, right? Error rates is one such interpreter. It takes in an expression that has any of those three language features, and it adds this log as the computation goes on. The way this is generally implemented in a language like Haskell is through using something called monads, and so the computation that it outputs makes use of Alchemy's monadic language feature. And then finally, we pass that to eval. Eval doesn't give us back an expression, but it does give us a result at the end. Okay, so Alchemy's testbed application that I alluded to earlier, we homomorphically evaluated a pseudo-random function. This may seem like a little bit weird. It sounds kind of like some crypto mumbo jumbo, or at least it did to me. But so why might we want to do this? So homomorphic encryption, kind of the idea here is that we wanted to take computational work away from the client without forcing them to give up their privacy. And however, if the process of encrypting something homomorphically is very expensive, then we haven't really accomplished this goal. So homomorphic encryption does happen to generally be more expensive, at least compared to other crypto systems, and the ciphertexts are often much larger than the original plaintexts. And ideally, we want to minimize the client effort. And so what we can do here is have the client encrypt their data, X, under some pseudo-random function. You can think AES or something like that, and encrypt the key for that pseudo-random function under the FHE scheme. So importantly here, their key is much smaller than the data they actually want to encrypt. They can then send both of these things to the server. The server, if it can evaluate the PRF homomorphically, what it can ultimately do is combine these two things together and get the data encrypted under the FHE scheme. It can then, from there on, this picture is exactly like the first picture of this form that I showed. Once it has the data encrypted under the FHE scheme, it can evaluate a computation on it, send this back to the client, and the client can decrypt it. Importantly here, though the client did much less work than he would have otherwise, as he only had to encrypt the key under the FHE scheme and was able to encrypt the data more cheaply. So we compare we compare this PRF to two other prior state-of-the-art implementations. One was AES implemented homomorphically, and the other was a pseudo-random function called LowMC, which was actually designed intentionally to be usable with fully homomorphic encryption operations. And then we're comparing that to ours, which is based on ring LWR. Each of these first two were implemented in C++. Ours implemented in Haskell. Okay, so in terms of execution time, the AES implementation took around 4 minutes. However, it operates on many blocks at once, so this comes out to be 2 seconds per block amortized. LowMC took 14 minutes, which corresponded to 1.7 seconds per block amortized, but ours takes 10 seconds period. So that's unamortized, and that's actually completely unoptimized. And so that's a decently exciting result. In any case, that's a decently exciting result. But what we're really interested in, what Alchemy, the contribution that Alchemy made here was the size of the code that we actually had to write. How might that compare to the previous two implementations? Well, it's not like a thing that's super easy to compare. It's kind of an apples to potato comparison here. In part because both AES and LowMC were written in C++, and so that just has some differences from Haskell in terms of how concise the code ultimately is. And additionally, both AES and LowMC were implemented using a different underlying FHE schemes. They were implemented using HElib, which exports a largely different instruction set than does LOL, which the Alchemy is based on. But we can still compare orders of magnitude here. So the AES implementation came out to roughly 600-ish lines. Low MC was a little over 200, and our ring LWR was at just 20. And in fact, it can fit on a slide. This is it right here. I've elided very little from this. I've elided basically type annotations, and that's it. But this is the entire implementation of the PRF. What's going on up here? This is sort of the plaintext implementation of the PRF. So really, the interesting bit is right here. We generate our random PRF key. We compile the PRF homomorphically. We prepare the arguments, and then we give these back to the client. Ultimately, what we got here was a decently what ultimately could have been something very complicated, but we were able to write it very concisely and very neatly. So Alchemy is not perfect yet. Maybe one day. So some things that we need to work on would be to improve the GHC compile times, especially with newer versions of GHC. For those who don't know, GHC is Haskell's compiler. We'd like to fully automate the selection of FEG parameters. Currently, the user specifies a pool of parameters, but really, there's no reason that Alchemy couldn't pick these parameters itself. We would like to support alternative backends. This would correspond to implementing a new language feature and maybe a new interpreter. But Alchemy is modular and extensible enough in order to do that. And then finally, we'd like to provide more higher level plaintext operations. So Alchemy has more of the appearance of being programming in a higher level language rather than sort of a more lower level assembly. Thank you very much. If you want to look at the code, it's all available there. Any questions?
Hi, I'm Timothy Birchfield. I'm from the University of Notre Dame. I loved your talk. That was really awesome. And one quick question I had is that it seems like, for the most part, there are types of computation that cannot be represented just with fully homomorphic encryption operations, especially in a circuit. Like, for example, non-terminating computation. Mm-hmm. I was curious as to whether or not I was missing something with the type tagless final, or just in general, how does your Alchemy handle that?
Yeah, so you wouldn't be able to implement a non-terminating computation. So it would have to be some computation that has a bounded size, so it's a circuit with some bounded size. But outside of that, there's little limit to what you could implement in Alchemy, with varying levels of difficulty depending on the operations that Alchemy natively supports, right? So with a larger library of higher level operations, there's very little that you couldn't support, but non-terminating computations would be one of them.
Hi, thank you. I thought that was...
No.
Great talk. My question is, what is the back end of the homomorphic encryption used in the current version? I mean, because LOL is not implement any homomorphic encryption, right? You use LOL to implement a back-end homomorphic encryption and use it as a back-end, right?
LOL is the library that we use for the homomorphic operations.
In my understanding, LOL just provide some operation above the ring, and you have to use that to implement your homomorphic encryption, right?
Oh, I see what you're saying. Yeah. So LOL does implement LOL does export in a separate package applications of the what's the word I'm looking for? Sorry.
So my question is, what kind of homomorphic encryption you have used for the current version?
It's called the library LOL. There's a sublibrary called LOL apps, which exports the necessary FAG operations. That's what we use. Sorry.
Okay, thank you.
Okay, so I guess I have a couple, but maybe we can take off. Like the most important, why Haskell?
Why Haskell?
Because you say easy in the title, right? And yeah. Haskell and easy.
Okay, fair. So one of the main reasons is Haskell's super strong type system. So we can make a lot of really strong static guarantees with Haskell. So as I mentioned, like the noise rates for each ciphertext is tracked statically at compile time. So it's encoded in the type of the ciphertext. And what that means is like if you give us a pool that doesn't have enough parameters or doesn't have large enough parameters, then that results in a type error. And none of this none of this ends up being a runtime overhead. Additionally, Haskell makes it really easier than some other languages to implement DSLs. So, in fact, the type tackless final style, which makes it very easy to implement modular and extensible DSLs, requires it requires at least as we've implemented it, requires lots of Haskell. Not necessarily Haskell specific things, but Haskell would be the largest language that supports them, like higher-kinded polymorphism and things like that.
Yeah, and you call it a compiler, but it's just GHC to compiler, and you're just writing on top like it's Haskell, right?
Yes. So the PGCT is a compiler from our DSL that's embedded in Haskell to another DSL that's embedded in Haskell.
Cool. Thank you very much.
Okay. Thank you.